Okay, now I am showing this thing to you. This is your text. That first thing that we discussed in chapter 1 is actually we started with a simple differential equation of first order. Then we approximated the derivative by using two function values separated by a distance in terms of independent variable, and that difference is called a step size. And you know that whenever we have our step size defined and we know the value of the function at the beginning and end of the step size, then using these two values, this slope can be actually estimated. With that estimation of the slope, you can proceed with solving the differential equation. Actually, our thing is that we have to find y. So if we want to find y, then say your function is changing in this way. You have two values there at these two locations. One is at xi plus 1. Another is at xi, just reverse. This point is xi, this point is xi plus 1, the independent variable, and this difference is what? Is it not a step size?
Yes,
Then
sir.
if the value of your function, say this is y, is known to you, this is yi, and this is your yi plus 1. Then what you can do, this derivative can be approximated as your yi plus 1 minus yi divided by xi plus 1 minus
Minus X.
xi, and then yi divided by 8. This is step size. Now, if we put this thing there, then what will happen? It will be equal to yi minus yi plus 1 minus yi divided by h is equal to f. Now, where to calculate this value? Actually, this value is calculated at the beginning of the step. Say xi at yi. Okay, one important thing is that you see the derivative here, the differential equation, the right hand side is the function of both your independent variable and dependent variable. If we proceed in this way, then if we solve for yi plus 1, then yi plus 1 would be equal to yi plus what? F into xi yi multiplied by h, isn't it?
Yes, sir.
And that f xi and yi, is it not the slope of your function at point xi?
Yes, sir.
Because
Yes,
this
sir.
is the thing. So you can consider this as your new value. This is your old value. This is your slope multiplied by a step size. This is not that equation, isn't it? So if we put that equation in this way, this type of algorithm is called one-step algorithm. In that one-step type algorithm, actually, most generally, that one-step type algorithm will have a function phi that is generally actually the estimation of the slope. If that estimation is made perfectly, then your solution will be going closer to your actual solution. And if this approximation is made in a crude way, then your solution will be erroneous type. Another issue is that not only the slope, your step size is one of the important factors, H. You can easily say that if your H can be kept small, then what will happen? The approximation of the slope will be better, isn't it?
Yes, sir.
And your solution will be going closer to your actual solution. So this algorithm is generalized into a form of a algorithm family. That family is called Rangakutka family, okay? lots of algorithms are there in Ranagutta family. All are one-step type technique. But the difference between different values of your different technique is in terms of accuracy that depends on approximation of the slope or sometimes called incremental function. So this is the Euler method that you already know. That in the Euler method, the technique that we discussed here, just a few, this technique is actually the Euler method. Okay, where your slope is approximated. We may call it a naive Euler technique, where your slope is approximated at the beginning of your 25.1. And because of this approximation, we will have some error always incurred in your solution. That error estimation is given there. If we are at a true value, and our predicted value will be something like this, as a result, an error will be there in our solution. We'll be illustrating this thing by using one of our examples. An example is there, is very anonymous type. But in our case, what I have emphasized from the very beginning, that we have to relate our problem to our engineering problem we learned so far. Otherwise, you will not feel the importance of your numerical technique or the mathematics in your course, okay? So let us start with the example that I have shown at the beginning of this course, and I am again just reviewing the thing just to show you how Euler method can be used to solve a differential equation and how the error can be seen if the analytical solution of the differential equation is available with us. So let me share the white screen. Okay, our problem we started with is a simple, for example, say an RC network, RL network. In this RL circuit, okay, if we apply a DC voltage there or an unit step voltage there, say this voltage is this, and amplitude is 10, and this is T. We usually call it 10 UT. That means this voltage is applied at T equal to 0, and you have to find the current flowing through your circuit IT for time T is greater than equal to 0. And assuming that your inductance is not carrying any initial current in it before application of the source, then analytically we know the solution of this. Say R equal, consider this value L equal to 1 Henry and R equal to 2 ohm. In this case, you know that your IT would be equal to what? E divided by R, base 5, and 1 minus e to the power minus R by LT equal to 2T. This is what the value of the current for time T is greater than equal to 0 for this circuit, isn't it?
Yes, sir.
By using simple analytical
Yes,
technique?
Yes, sir.
Okay, then if you want to solve this equation by using numerical method, then how to do that? You have to write the differential equation, isn't it? We know that the differential equation relating the current and voltage of this circuit is this. And if we solve for di by dt, that di by dt would be equal to E minus Ri divided by L, isn't it? And if we
Yes,
put
sir.
the value that we assume, then it will be equal to 10 minus 2 into I, isn't it? This is what our first order, this is our ordinary differential equation that we have to solve. This equation is very similar to dy by dx is equal to fxy. In our case, our independent variable is time. Our dependent variable is current, isn't it?
Yes, sir.
Yes, sir.
That if you want to solve it, what you need to do, first thing is you have to select what? You have to select step
Yes, sir.
size. That what time step you are using. consider the thing. Be careful about something beforehand. Otherwise, your approximation for a step size will not be, for example, prudent enough so that you will obtain a viable solution of your numerical problem. In this case, you see that we know the behavior of this inductor current, that if you plot our analytical solution, we will see that this solution will take this shape. The steady state value will be equal to 5 ampere, isn't it?
Yes, sir.
And we
Yes.
know a value of time characteristic time, we call it time constant. What is the time constant of this circuit?
Sir,
Is
R
it
by L.
not equal to
A by L by R.
Oh, sorry, sir. L
L by R? Okay. So in this case, our time constant is half second, isn't it?
yes, sir.
Is equal to 0.5 second. Now you know that time constant is that value of time at which if your current is increasing, your current will reach at a value. That value is around 67% of your maximum value. What you can do then, in order to find these steps, what you can do, you can roughly use a thumb rule that you divide your time constant by 5 steps. As a result, what will happen? You can consider that your age can be thought as 0.5 divided by 5 is equal to 0.1 second. You got my point?
Yes, sir.
Can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
So
Yes,
if
sir.
your time step is equal to 0.1 second, then can we proceed with calculating this numerical current for each step of your time, starting from an initial value numerically? For example, here you consider that your age is equal to 0.1. If your age is equal to 0.1, then you know that your differential equation di by dt is equal to what? 10 minus Ri, isn't it? R equal to 2. So it is 10 minus 2 into I. Now, according to our Euler algorithm, we are, if we have a time step, for example, say our initial step is this next step is this, next step is this, next step is this. This is 0.1, this is 0, this is 0.2, this is 0.3, something like this. So if you want to find, for example, a general algorithm for this, our algorithm will be equal to what? I at I plus 1 time step would be equal to I at plus 10 minus 2 into I of I time step multiplied by step size. Is it not?
Yes, sir.
Yes, sir.
So if this is the case, we are assuming that at time step 0, your current is equal to 0. So can we proceed in calculating, for example, this thing, say you time here, now your current is there at time t equal to 0, your current is 0, your current I 0.1 is equal to what? I0, 0 plus 10 minus 2 into I0, 0 multiplied by 0.1 equal to not yes, equal to what? You understand this equation?
Yes, sir. 1.
Yes, sir.
Is equal to 1 ampere, isn't it? So this is your 1 ampere. And if we want to calculate, for example, at 2, that is equal to what? That I01 plus 10 minus 2 into I0.1 into a step size 0.1, isn't it? And that will
Yes.
be equal to 1 plus 10 minus 2 into 1 multiplied by 0.1 is equal to what?
1.8
Equal to 1.8 what? Ampere. Okay.
ampere.
So this is, so at 0.2, this is 1.8 ampere. So if you keep going on calculating this thing, can't you, for example, find how your current is growing with time? Then you can plot, for example, this curve with your analytical curve to show, to know how these two solutions are corresponding. Okay, you can write few lines of your MATLAB program, or even you can use your Microsoft Excel for this type of problem without coding anything. That you can just solve this type of problem very simply. Have you ever used Microsoft Excel to solve this type of problem earlier?
No, sir.
No idea about it.
No, sir.
The thing is that nobody will, for example, give you everything ready for you. Okay, what you need to do, you have to explore the thing. Okay, engineering students are not passive. They should be much more active than their teacher. Otherwise, you cannot be the student of this age. Okay, just it take about 2 minutes to do this thing for me in this morning. Okay, as simple as this. Actually, what you can do, you can set a column there. That column will be your time. And we consider that our time step equal to 0.1. So it is 0.1. Then you fill it up to the point you want to calculate. Okay. The next step is what? Next step is you have to put the equation. For example, say, let us find first the analytical equation. You know, the analytical equation is simple, something like this. Is it not your analytical equation? 5 into 1 minus
Yes, sir.
exponential 2 into why I writing here A2? The reason is that your A2 is the address of the time. Okay, when you are putting A2 there, that means you are taking this time that is present in your A2 cell, and that is equal to 0. Okay, so you will have your current 0. Then what you can do, you copy this, for example, formula, want to go. Then this will give you the analytical solution. Okay. If we plot them, you will see that this is what that plot, the analytical one. Okay, you can easily see that when I take this, your independent axis is there, time axis, this is there in time, and your solution is plotted with this gray curve. So this is your analytical solution. Okay, you know this solution. Now, next thing is what you have to calculate a numerical one. But if you want to do it by hand calculator, for example, it will take longer time. To do that, what you can do, your time step is already defined, then you just put your algorithm there. Your algorithm is equal to what? Your algorithm is equal to the previous value that is there present in your B2. Okay, that this value value of your current that is present in your previous calculation is equal to 10. That means your value of your voltage minus 2 into the previous current multiplied by the step size 0.1. Do you understand this?
Yes, sir.
Is it not? It is not your Euler formula, because you have to bring your previous current. That previous current is stored in B2 cell. Okay, that you are replicating using for your subsequent calculation to find the current, new current that will be stored in your B3 cell. And that current will be used for your next step to calculate the current of your B4 point. At point 2, you see that gradually your cell address is changing and your current you are calculating. So if you go in this way and copy this formula all the way up to your last time step, then you will find your solution is there. Okay. Then you see that this orange curve or red curve is nothing but the analytical solution. Can you find the closeness of these two things? And
Yes,
how
sir.
close they are? Okay. Then if you want to find the error, how can we do that? You just find the difference between these two cells. Your C cell is your actual value and your B cell is your calculated value, isn't it? By using
Yes, sir.
numerical technique, then you make the difference. That will be your error. And you see that almost all the cases, you see your numerical value is lying above your analytical value. As a result, your error will become negative. And if you want to plot the error, you see that your error is changing in this way. Okay, this is a very simple something. Anybody can experiment on it to visualize the thing. I don't know how many of you actually are considering those things very seriously. If you cannot do that, you will never, for example, feel the joy of learning. Okay, you got my point? What you can do, you can easily change this, for example, value just to know the effect of your what we call step size. Consider that we are now making our step size 0.2. Then what you can do, you just simply replicate the thing with a step size equal to 0.2. You see that your time will be doubled here, almost 11.6. And your calculation is there. And as this calculation was not made up to this, okay. Then you see that your current reached at the steady state for your analytical cases, but because steady value is 5 and other things are there. Can you now consider that because of this step size, what happened?
Yes, sir. So the error has increased.
Error increased, and by error is going from negative to positive. Okay, and you see that how your error curve is now changing. Okay, in this way you can easily experiment the thing if you can do that. Okay, how many minutes it will take just to write the formula and replicate the thing? Okay, this will take few minutes to solve any type of problem. Okay, of this type. Okay, you can simply, for other problem, you simply change the formula and proceed with it. But selecting the time step is actually a crucial something, because if you can select your time step that is not prudently set, then what will happen? Your error will be gradually increasing. Even if you can make your time step, for example, say more half, for example, say 0.5, then if you want to proceed your calculation, you can easily see that what happens. Okay, I am not showing that thing to you. Okay, you see that again your error is something like that. Oh, it is not replicated actually. Okay, you see that the error is there. Not always that your time step may improve. Okay, you can experiment it by changing your time step, then see what happens. So this is a very simple recursive type algorithm, and you can do that. So this is actually very naive step of solving differential equation, the Euler technique. Now, what it has been discussed earlier, that all other techniques actually of one step type approximation belongs to a broad category called Runge-Kutta methods. Euler method is one of such methods and the most simplest one. Then this method can be further improved by approximating the slope in a different way. Okay, that approximation is made in your, okay, some examples are there with some discussion. You just try to go through it to know how your Euler's methods are working with. Okay, step size have been changed and how the solution is improving and going closer to your actual value. This is also there. Okay, you have your two types of error, truncation and round up error. Both error will be involved in your Euler method, and the error estimate is also made. The error approximation error will be the order of step size. So if we increase the step size or half the step size, your error will be quartered, something like this. But this is not a very general conclusion. It also depends on some problem. Later we will see that we have a class of differential equation that are called skip type, where a broad variation of current will be associated with a very finer variation. In that cases, some modification of the algorithm will be needed, otherwise they will not work. So this is actually your Euler method is nothing actually. It arrived from the Taylor series approximation. You considered only the two terms of the Taylor series to derive the differential equation. Now the thing is that if we want to go to the modification, your modification is all algorithms are there. If you want to program it, program it. Some examples are there. Those examples are of mechanical type. But our example, a similar example we have chosen, that is our RL circuit, this equation and equation E25.4.1 mathematical solution nature is also same. Because of the parameter values, sometimes some problem error will be different. Okay, now the modification of our Euler method, that modification is made and it then it made by Huygens. For this region, this method is called Huygens method. What is the difference between the naive Euler method and Huygens method is that in the Huygens method, actually, what I have discussed at the beginning, that all this belongs to a broad class of 1-point type algorithm. They are called Rangan-Kutta method. And the difference of different variant of this method depending on the approximation of the slope phi, and that is sometimes called incremental function. And that incremental function is approximated at the beginning point of each step of your calculation for the case of Euler method. And in the Huygens method, this incremental function of the slope is calculated at 2 points, one at the beginning, another at the end point of a particular interval. And then the average value of this slope is taken as a value of the slope that is assumed to be remaining constant within the interval. That means your slope is calculated at the beginning, your slope is calculated at the end, and these two slopes are averaged. Then this average slope is assumed to remain constant within the interval of calculation. Okay. Now the question comes how to, because your initial values will be given. By those initial values, you can calculate the slope at the beginning. But if you want to calculate slope at the end of the interval, you have to know the value of your function. Otherwise, you cannot calculate the slope at the end point. For this reason, what it has been done in the Huygens method, first the slope is calculated at the beginning. Using that slope, the function value is calculated like you by using the simple Euler technique. Then using that, if the method were Euler, then we would have stopped at that point. But as the method is not Euler, for this reason, this is an intermediate step where a value of function is calculated, and that value will be used to calculate the slope of the function at the end of the interval. Then you have your two slopes available then, one at the beginning, another at the end. Then you take the average of these two slopes by adding them together, dividing by 2. Then you proceed with what is there in the equation, yi plus 1 equal to yi plus phi into s. Your phi would be the average of the two slopes, one at the beginning, another at the end. The end slope is calculated by using an intermediate value of your function. That intermediate value is calculated or predicted by Euler's technique. This is what the modification of the Euler method, and it is called Huygens technique. Okay. So if you want to proceed with our formal way to proceed with, then you see that your slope is calculated at the beginning yi xi by using 25.1 2 as usual. Then this value of the slope is used to calculate the value of your function yi plus 1. A superscript 0 is used there to signify that this is not the final value of your solution. If it were final, then it becomes the Euler standard Euler method. But as it is not final, what we do then, this value yi plus 1 0 will be used to calculate the slope at the end point xi plus 1. So this equation, the intermediate one, is called a predictor equation. Then you see that this whole process is described there. I hope if you engage properly, you will understand what is there in this figure. You understand the discussion?
Yes, sir.
This is what your starting point. This is your starting point. If this is your starting point, your slope at the starting point is calculated, okay, with the help of starting value of your okay. In general, what will happen? We will have to begin from a starting point. That starting value of your function yi and xi will be available to you. Using these two value, you calculate the value of your function xi, yi. This is nothing but the slope at the beginning, okay? This is at this point, the slope. Now, if you want to calculate slope at the end, for example, if your slope will be remaining the same for conventional Euler technique, then this is what the path we are moving. But what we have done here, we are not finishing the calculation at this point. Rather, we are moving to the point xi plus 1 with a value yi plus 1, 0 that has been calculated using this slope by using Euler method. So once this value is available to you, then at this point you can calculate, because you see in calculating the slope at point xi plus 1, you need a value yi plus 1, but your exact value of yi plus 1 is not available to you now. For this reason, by using Euler technique, this value y0 is predicted first by using the initial slope. Then this is what the slope at where? Slope at the end point of the interval, isn't it? Is it okay?
Yes, sir.
Yes, sir. Yes, sir.
I cannot actually identify whether you are there or I am disconnected.
Sir, can
So
you
this is
hear my
what the
voice?
value is calculated at the end point. You see the slope is getting in this way. So then, as we are moving to a point with a new slope, then our approximation will be taking in form. And actually, where I am activating the annotation, then scroll. Sorry. Yeah. What is with you? Hey, am I audible to you?
Yes,
Sir,
sir.
maybe our voice lagging. Yes, sir, you're audible.
Yes, sir, you're
Maybe.
audible, but your voice is cracking.
Sir, it is lagging a lot, sir. Actually,
Sir, there is some lag
This
in your
might be
voice.
the
answered after
problem
a
from
long
my
time, sir.
end, and even it. So I have no way to improve this thing. For this reason, you have to bear with it. That might be a problem from my end, and can be also a problem from your end because of network issues, isn't it?
Yes, sir.
So our discussion was what about the calculation of the slope, isn't it? So we are calculating the slope at the beginning. We are calculating the slope at the end, and you are taking the average values of the slope, and that average value of the slope will be used to calculate your yi plus 1. All this process have been summarized in these two equations, equation 25.15 and 25.16. The former equation is called the predictor. The former equation, that is 25.15, is called predictor, and 25.16 is called corrector equation. Okay. How to apply them in problem solving? This is very simple. You can also experiment it with the example that I have shown to you, or even an example is there in your book. You can proceed with this example. Okay. but try to let me explain something more on top of it. What is there in your example? Okay. See the equation takes intermediate value equation and next time step, isn't it?
Yes, sir.
Is the situation is improved? Hello, guys.
Yes, sir.
Sir, we can hear you.
But I cannot hear you. I don't know what is the problem. Getting tired, okay? A network is one issue. Another issue is sitting continuously in the chair for hours together is another issue for me. Now is it okay?
Yes,
Sir,
sir.
it's
We can
okay
hear you,
now.
sir.
We
Sir,
can
can you hear
hear
us
you.
at this instance?
Yes, I can, but again, the same problem is there. Okay, your voice is getting distorted. Let me continue. Okay, to
So
another
there is a
step.
lag actually, sir. We are responding, but sir, the response is going after a long time, sir, to you, sir.
Long time. But now it is okay probably. Can you hear me now?
Yes, sir.
Yes, sir.
Yes,
It's
sir,
okay
we
now.
can hear you.
Okay, then your equation 25.15 is a predictor equation. You see, where a function value is calculated at the intermediate point, then this value is used to calculate the slope at the end point. Then they are averaged together to finalize the value for that point. Okay, in this way you can proceed. You see in equation 25.16, your yi plus 1 and yi plus 1 are they are both in your left hand side as well as your right hand side, isn't it?
Yes, sir.
If this is the case, then what you can do, that character equation can be repeatedly calculated for a particular time step to refine the value yi plus 1. This is illustrated there in this example. Okay, let us redo the thing, then it will understand. You will understand the thing. This is what your differential equation. Can you see the differential equation? Y prime equal to 4 e to the power minus 0.8x minus 0.5y.
Yes, sir.
Yes, sir.
This is what a differential equation, okay? You see that in your differential equation, both your what do you call your left right hand side, actually this is what is the order of this equation? Is it not a first order one?
Yes, sir.
It is a first order
Yes, sir.
differential equation, isn't it? And you see that in our general derivation, that was thought as x a function of xy. That means the function of both your independent variable and dependent variable. Okay. So in this example, your dy by dx equal to what? 4 e to the power 0.8x minus 0.5y, isn't it? So is it not the function of x and y?
Yes, sir.
Am I audible?
Yes, sir. We can hear you,
Yes,
sir.
sir, you're on.
কিভাবে সম্ভব এইভাবে এই ক্লাস নেওয়া কন্টিনিউয়াসলি ফ্লাকচুয়েটিং? ওকে, প্লিজ বিয়ার মি। হ্যাঁ,
আজকে অনেকগুলো আইএসপি সমস্যা করতেছে।
actually in Uttara you see many of the networks have been, for example, disconnected. I don't know because of this problem, what is the problem with this thing? So you have to bear with, no problem, no way. Actually, the thing is that if you, okay, your initial, you have to calculate the, your initial values are given there. And you have to calculate the, solve the differential equation from x equal to 0 to x equal to 4, okay? Now, your, with a step size equal to 1, that means your h is given, h is equal to 1. And the initial value is also given. So according to our Hughes method, what you need to do, you have to calculate the initials. Okay, the analytical solution is also given. So using Hughes technique, what you can do, in Hughes technique, what you need to do, you have to calculate the slope where? At the initial point, isn't it? Our initial point is x equal to 0. At x equal, this is, you can consider that this is your xi, this is your yi, okay? So using this value, if you put this there, this is what your slope. Next step is what, using this slope, you have to calculate a value yi plus 1 0 by using your Euler's method. And that will be equal to, in our case, that will be equal to yi plus slope you calculated multiplied by s. In our case, we are starting from the beginning. So our step size is equal to 1. So our value will be equal to this. yi plus 1 0 would be equal to y1 0. And that value is calculated there. Next step is what? Using this value, we have to calculate the slope at the end point. End point was, initially we calculated, this equation is actually calculating the slope at x equal to 0. Using this way, we have to calculate the slope at x equal to 1. If you want to do that, what you need to do, again, you use the same equation just to calculate the slope y prime at x equal to 1 with the help of y1 0. So this is what your slope at y1 0. Okay, the general equation is also written there just to make you understand that how the algorithm is being used here. This is the general expression, okay? As this is what you slope, not the value of your function, okay? This is your slope at what? X equal to 1 using what? Using y1 0, isn't it?
Yes, sir.
So this is what the slope, okay? Next step is what? You have calculated your slope at the 2 point. One is at x equal to 0, another is x equal to 1, okay? This slope should be averaged. This is what that average slope, okay? So once this slope is averaged, then you can calculate your value y1. Your y1 would be equal to your y initial y. That means general expression will be equal to what? yi plus 1 would be equal to yi plus this average slope multiplied by h. In our case, as we are at the beginning, it should be equal to y1. y1 would be equal to y0 plus average slope multiplied by 1. Our average slope is calculated as this. No, 4.7 this, okay? So this is what this value. Okay, this is your initial value y0, and this is the average slope. This is your step size. So this is what the value of your variable at where at x equal to 1. Now the thing is that as your character equation 25.16 was actually an iterative type equation, where you can also at this time step x equal to 1, you can further refine your solution by using this value. You calculate again the slope and proceed with refining this thing. Okay, just you simply put this value to the to equation 25.16 repeatedly, so that you will have a value that is more refined in successive iteration, so that you can proceed with calculating a new value. This is illustrated in this equation. So you see that here in this equation, your y1 is again calculated. Y1
Sir, your sharing
is
is stopped.
stopped. Getting tired actually. Okay, in this equation, you can easily do it. Okay, please try to go through it and let me know you understand it. Okay, what it happens that this predicted value is again used there to calculate the slope, and is because the upper equation is the average of two slopes. Okay, then again it is divided by 2 to get the average slope, and again calculated there. So if we keep going and repeating this calculation for this time step in the character equation, then you will have a value that is more closer to the actual value. But if you do not want to follow this, what you can do after having this thing calculated, you can just go to the next time step, then proceed with your solution. Okay, but the algorithm will be simpler. The reason is that if you have your slope that becomes the function of both your dependent and independent variable. In this case, this repetition or iteration in the character equation can be used. But if your function is only a polynomial type, and it is the function of independent variable only, then you can simplify your algorithm by using this thing 25.18. It is simply equal to yi plus 1 is equal to yi plus the function values, that is slope at point xi and slope at point xi plus 1 divided by 2 multiplied by x. In this way, this is something like you can easily consider this portion. Is it not very similar to your trapezoidal rule? This equation is not similar to trapezoidal rule?
Yes, sir.
Because if we have an integration, for example, which will limit x1 to x2, x1 to x2, and this is what your function, because we are by solving our differential equation means we are simply integrating it between two times within an interval, x1 and x2, we are simply integrating it in this way. Okay, for general case, you can say it I, and this can be your I plus 1. Okay, for the general case, what is that integral actually? Our purpose is what? If we are at the interval between xi to xi plus 1, then you have a left hand side, for example, dy by dx, and is equal to, in our case, it is the function of independent variable only. Then can we arrange this, rearrange the thing in this way? Dy is equal to f xi dx, isn't it? Then we can easily, for example, differentiate it between two time interval. This is at, for example, I. This is at, say, this is, you say yi, and this is your yi plus 1, and that will be equal to what? Integration xi plus 1. This is your f xi fx dx. And can we approximate this integral by trapezoidal rule by calculating the value of the function at xi
Yes, sir.
and calculate the value of the function at xi plus 1 divided by 2 multiplied by h. So this equation is actually a repeated application of the trapezoidal rule at each of the interval, and your value is updated in each of your iteration, as you know that it is integration. Okay, your previous value is added with the your new value become a previous value with some incremental value added with it to get the solution. So this is there expressed in. Then we have another variant of this rule is called midpoint rule. Okay, this is actually what I have talked earlier, that calculation or refinement of approximating the slope function phi is actually the main issue here for your 1-point method. Okay, in your Euler's method, it is calculated at the beginning. In the Hewens method, it is calculated at the beginning and the end. And in the midpoint method, actually, your slope is calculated at the midpoint. Okay, in this way, that this is what equation 25.5. 25 is nothing but your Euler's rule. It is not Euler's rule, but it is applied where? It is applied at the midpoint between two intervals, isn't it? Can you identify the equation here? Your I plus half means actually this signifies that we are calculating if this is your I, this is your I plus 1, then we are here, that is I plus half. Okay, that means midpoint. Okay, where your interval will be halved, h divided by 2. You see that your slope is calculated where? At the beginning. And we are multiplying it with h by 2. This is nothing but your Euler's rule with a step size h is replaced by h divided by 2, isn't it?
Yes, sir.
And here in this case, we'll be obtaining a value y. Our objective was what? Our yi is already with us. We have to find yi plus 1. But without going to y plus 1, we are calculating yi plus half. That means we are calculating the value of y at the half of your interval. Then this value can be used to calculate the slope at this point. That means we are here at xi, where another function is there, say xi plus 1. Then initially this was the slope. Now we are calculating our slope at this point. Say this is your slope at where? And this point is actually at xi plus half, midpoint. And that slope is assumed to be remaining constant within the interval xi to xi plus 1 to calculate the value of yi plus 1. So the difference between the previous one and the next one is what? In the previous case, your slope is calculated at the beginning and your slope is calculated at the end. Then average value was taken. So here in this case, your slope is calculated at the midpoint. In order to calculate the slope at the midpoint, you need to know the value of your function at the midpoint. Because slope at the midpoint will be equal to f xi plus half into yi plus half. Your xi plus half will be available to you, but you do not know the value of yi plus half. That yi plus half is nothing, the value of your function calculated by Euler's theorem, Euler's rule, with h equal to h by 2 using equation 22.5. So up to this point, it is Euler's rule. Next, once your y plus half will be available, then we calculate the slope at the midpoint. Then using that slope, we use our Euler's rule to find the value yi plus 1. So this is what your midpoint rule. It is not very difficult to understand, very simple. Okay, all these things are explained there in this figure. Your algorithm is this. Okay, your slope at midpoint is calculated by equation 25.26. And your slope, and next, once this slope is available to you, then we apply our Euler's rule, replacing your slope function phi by f xi plus half yi plus half. This is the slope at the midpoint. Then you multiply with the step size. In this way, the midpoint slope is used to calculate the value for the next time step. So this is your modified form of Euler's rule. It is called midpoint rule. Okay, a summary is there, and some what we can do. Okay, I can ask you something to do at this point if you want to do it. Okay, an example is there. I have already given to you. Rather than doing a fictitious example, which is there in your book, you can have an RL circuit or whatever electrical system you have learned in your earlier level that involve differential equation. You pick a first order differential equation from them and try to apply these three variants there. Okay, the first standard or naive Euler's. Then you can use your Heron's technique there, where average slope is used to find the value of your function. Then you can apply your midpoint slope there to calculate the same, to solve the same problem. With the same step size, you can proceed with calculating using these three algorithms. Then you plot them. You can either you can program them, or even your Excel sheet is enough to investigate this thing. You can easily understand the performance of these three algorithms for a single problem. Now we are going to the generic discussion on Runge-Kutta methods. This is the general actually discussion. The derivation is actually a bit complicated, but it's still not unmanageable. You can do it if you can afford some time, but we will be knowing, not giving that much time in deriving the thing. The reason is that those things have already been derived, but we need to know the meaning of the thing there. Okay, how those things are involved. In the general category of the method, we call them Runge-Kutta method. Then you will see that by setting some parameter values in Runge-Kutta general method, you will find Euler's method there, you will find your Heron's method there, midpoint method there, and some other methods are also there. Okay. So this is your function 25.28. It is rewritten from the equation 25.1 in the form that you see that now what we have discussed earlier. Okay, the variance of the method is actually depending on how the slope is estimated. As your slope will be a function of a step size for this region, this slope phi, that is generally called increment function, will be the function of x, y, and the step size. And the way how we calculate this increment function is actually the main thing, and the different methods depending on the way how they have been calculated. Okay. In the general Runge-Kutta method, your phi can be expressed as a function as a polynomial, something like this, where A1 and K1 are the thing that we need to find. Okay. Your A1 and K1 are defined in this following equation. I am simply giving a look there, you can proceed with. Okay, K1 is actually what? K1 is nothing. Is it not the slope at the very beginning of your point, at the begin point, at the beginning of the interval?
Yes, sir.
Okay. Then if your K1 is slope, then your K2 will also be a slope. But that slope is calculated, you see, at a different point. You see that your X value, that means we are not at the initial point. We are progressing from the initial point forward. Is it not something like that? We are increasing. If you are at this initial point xi, we are going here at x. Now this point is your xi plus p1 into h, isn't it? That means some portion of your step size is added with it, isn't it? Okay.
Yes,
Yeah.
sir.
At this point, let me ask you one question. If your p1 is equal to half, what will be the name of the method? Is it not the method just we discussed few minutes ago? The
Sir,
midpoint
the
method?
midpoint method, yes, sir.
Where your slope will be calculated at the midpoint between two intervals. Because our xi is there, we are putting, you say this point is xi plus 1. So we are moving towards xi plus 1 by tuning the value of p. Isn't it p1? Okay. Now, in calculating, for example, the value of the slope at xi plus p1, you need the y value. This y value is augmented in this way. Your y value would be equal to the y value already available with you with a coefficient q11, k1 into h. Previously, you see that if this is a simple case for Euler method, you see that the value of your q11 would be equal to 1, isn't it?
Yes, sir.
Because your yi plus k1 is your slope multiplied by h. So in this way, you can think that gradually your slope is approximated, okay, in such a way that we are progressing towards the end of the interval and approximating a slope, for example, gradually by changing the value of P1 and P2, and we are adding the function value. That function value is also added with some coefficient. Then if you want to proceed in this way, then you will find a very general formula. But the main question is here, how to find the value of P's and Q's. YOLO. How to find the values of P's and Q's. Okay, there exist many ways to find the values of Q. Some are illustrated there with a lesser complex problem. For example, second order Runge-Kutta method. In the second order Runge-Kutta method, we will have our two values of K. Hey, are you saying something there?
No, sir.
No,
Who is
sir.
talking
Your,
there? Second.
no, sir.
Yeah?
Your voice is going there. It has an echo.
So there you keep your mic off if you want to just avoid the echo. So this is you. That means somebody is using loudspeaker to hear my voice. Okay, in your second order method, we will include our two values of K1 and K2. Okay. In K1 and K2, how many parameters will be involved? You will have a parameter P1 and Q1. Okay. And a derivation is there. I am leaving this thing to you to go through it. I hope you will understand it.
Sir,
So once this thing is available, you will see that. Okay.
sir, I have a
If you have
question.
a question, what question?
Sir,
Ask.
here it is a second order method, but sir, we are ultimately solving first order differential equation, right, sir?
The name of the method is second order Runge-Kutta method, but we are solving first order, of course, first order. Because as you see that a single slope is involved there, what does it mean? It means that we are dealing with first order, a
sir.
single equation. We are solving a single ODE of first order type. Now this method will be extended further. How can we solve higher order method? Okay, but higher order differential equation cannot be solved in the form they are given. You have to translate them into a simultaneous form of first order equations. Then you can solve them. Okay, I will be talking about this later. Okay, no problem. So this is your second order Runge-Kutta method. It is not the second order differential equation. Okay, we are referring the same equation from the very beginning. So this is what my lecture for today. Okay, you will see that by putting the value of your A, you can have your Huygens method there. You can have your midpoint method there. Another variance of the new method you will find there with A2 equal to 2/3. It is called Ralston's method. All these methods are applied to the single problem, and the performance is studied there. Okay. Then from the next day, we will be discussing about third order and fourth order method. They are more generally used in solving differential equations. Okay, you stop recording. This is all from my part today.